Good afternoon, everyone. And my name is Ruiyao Yao. I'm from China, and I currently work for Baidu. And today, I will tell a story about how we deal with a huge amount of time series. And here's something about me. I'm a senior R&D engineer at Baidu, and I work on Baidu's biggest operation knowledge base, and it has 3 storage components. The first is TSDB, which stores all of the monitoring time series data, and the second is EventDB, that stores operation events like alerts, deployments, and other online operations. And the third one is MetDB. It stores name-to-IP mapping and service-to-service association and other meta information. Okay, this is today's agenda. And first, I will introduce the monitoring system at Baidu. And the second, what are the challenges of building a TSDB to meet our own requirements? And how the TSDB's architecture looks like. And then I will share some practices in performance tuning. And finally, how we ensure the availability. Here's something about the monitoring system at Baidu. The first question is, why do we need a monitoring system? And just imagine that a guy is at home and he wants to play some online games. And for example, he wants to get a chicken dinner tonight, and he's just about to play PUBG. But then, oops, he can't. And he sees this. He wonders if there is something wrong with the server or his home network. So what should he do next? And in China, you should simply visit Baidu.com. But he's not going to search for a solution now. He may do it later. And he's going to use one of Baidu's famous features other than a search engine. Just in case you are not familiar with, let me show you. See? No, not this page itself. To make it clear, let's do it again. You type www.baidu.com and then press enter. There you go. Okay, the trick here is when you cannot access Baidu.com in China, then you can be very sure that your home network is broken. And why is that? That's because in China, you know that Baidu.com is always available. So it can be used as a connectivity testing tool. And you can try it now. And you can rely on it. So the availability of our site must be extremely high for people to test their connectivity of their network, and whenever they want. And how can we achieve this? We definitely need a lot of mechanisms to help us. And first of all, we should understand our services very well by observing as many aspects as we can of our services. And so a monitoring system is, of course, necessary. It's the eye of reliability engineering. And with the help of monitoring system, we can know as much information as we can about our services, such as we can get host resource utilization like CPU, memory, and disk, and network, and how the OS is configured, how the RPC behaves, and for JVM program, the GC frequency and the heap usage, and our business PV, which stands for user requests and revenue. Or we can monitor any targets to get any customized indicators in each service. And the monitoring system helps us to improve availability in two ways. One is instant response. Engineers set alerts on the monitoring data to detect incidents. When an incident happens, engineers examine the monitoring data to find out the root cause. And second, it facilitates the capacity planning, and engineers analyze the monitoring data to tune performance and decide how many CPU or memory should they put into their service. All these above things need monitoring system to provide data. And our team built the biggest monitoring system at Baidu. It's an essential platform of operation, and our SREs use it every day. And the monitoring system collects metrics for every host, every service, and every instance. It helps watching our hosts and services in many ways. And it produces tons of monitoring data in the form of time series. So, what's the number? Roughly speaking, we now have millions of targets and over 600 metrics per target in average. And as time series represents a series of values of a single target-specific metric, the total number of time series we have now reaches 1 billion. So many zeros. And the number is still increasing. So all these 1 billion time series must be stored for the future use. And we store this data into a TSDB, a time series database. But the data scale imposes a huge challenges on our TSDB. What 1 billion time series bring us are that we now have 50 terabytes data generated every day, and the read and write throughput is around 10 million requests per second. In every second, the users will write 40 million points into the system and read 60 million points out. In terms of bandwidth, it's 50 gigabits per second of write and 100 gigabits per second of read. And there are still more. Some systems such as alerting wants to see the data as soon as possible, and it requires the data to be visible within 10 seconds. And the 10 seconds is the minimal data collection interval of the monitoring system. And for read, query response time should be less than 500 milliseconds at the 99th percentile. And further, as the underlying storage of the monitoring system, which is to help SREs to improve their services availability, the storage itself must be highly available, and we need to provide the availability at the level of 4 nines. So let's see how our TSDB's architecture looks like. Pretty simple, right? As we know, 1 billion time series come with a lot of write requests. So we should consider write performance at the first place. And thus, we choose HBase as the underlying storage. And it uses a log-structured merge tree, which assembles random writes in memory and to dramatically reduce disk I/O, so it can achieve a high write throughput. And HBase is used to save all of the time series data. And compared to write, read is really a different thing. And it's more complicated, and we will talk about it later. Here, we place 2 individual modules to process write and read, respectively. The writes are processed by the module called saver, and then saver will write data in batches into HBase. And also, server will buffer the writes in case that the HBase is temporarily unavailable. And the query engine answers read requests from monitoring system itself or the user. By separating reads and writes, both server and the query engine can get a more reasonable resource supplement. We also provide a front-end API service to let users retrieve data or push their own time series conveniently. It provides RESTful APIs. And for services of monitoring system itself, which usually require a higher performance, and services such as alerting can communicate directly with query engine to gain a better read performance. And also for agents that are deployed all over Baidu's servers can send metrics directly to server. This is the data layout in HBase. And there are two kinds of tables. One single data table that stores time series data, and the data point is identified by target, metric, and time and the value. And we set TTL of the table to expire all the data. And some other tables store meta information of time series, include metric properties like metric name and the collection cycle, or the value of the type of the value, etc. And some important metrics like business's PV or revenue, it may associated with several tags. For example, the ISP that provide networking infrastructure and the data center on which the service is deployed. And then, if we want to select the time series with a tag filter or to group the readout by a specific tag, we need an index table to store the association from tag to time series. And as the time series data points are collected in a constant frequency and sorted in time order, the design of the row key, HBase row key, should be optimized for balancing and read performance. The row key is made up of 3 parts: the hash of the target and the hash of the metric, and as well as a timestamp that is rounded down to 2 hours. It means each row contains 2 hours of data. And all these parts is of constant length. And the first 2 parts, which are hash values, make rows distributed across all servers. And the timestamp part ensures that points of the same metric stay together sequentially in time order. Let's say if the metric is collected every 10 seconds, then the column qualifier is the offset to the 2 hours round, and the value is stored in the corresponding cell. This design is inspired by OpenTSDB. You can find it in the link. And this architecture, this simple architecture, works very well. But things are getting tricky because we found the data amount increases beyond expectation. And the write and the read become heavier. We just cannot keep putting resources into TSDB. So we must do something to improve the performance. And problems are that we find a lot of large queries. They are very slow and also take up a lot of bandwidth. And for example, there is a team that is responsible for analyze the overall server resource usage of the whole company and will give a daily report. And it sounds like something normal, but you should know that Baidu have tens of thousands of hosts, and guys from this team just fetch billions of data points on each request. And here is another example. Some users want to see how their business's PV has grown last year, and it fetches millions of data points per request. And besides, as the monitoring system provides anomaly detection service, and the anomaly detection service issues a lot of small queries on recent time series data, and the data concerned only occupies less than 20% of all the time series, but these queries occupy more than 80% of all the queries. And then we investigated into the queries cases and found out that these queries fall into two categories. And one is latency-insensitive, and queries of this kind are usually short-term queries that involve a lot of metrics. And remember the bad guys. Or long-term queries that require high data resolution. And the other one is latency-sensitive. And queries from this category is often short-term queries that involve several metrics, but expect the data to be of high resolution. And this is the most case. Or long-term queries which don't care much about the data resolution. So let's get back to the queries cases. Now we can easily classify these cases. The first, daily resource usage report of all the hosts, is obviously latency insensitive because the daily, there's a whole day for us to process these queries. No need to hurry. And as for PV's growth trend of the whole year, it's not so obvious. But in one situation that user explore the trend chart via our web visualization page, and it can be seen as latency sensitive because people just can't wait. And it comes to PV's anomaly detection. Latency sensitive, of course. You don't want to get an alerting that tells you that your service has been down since last night, right? So we have found out the queries patterns, and then we can do some specific tunings. And firstly, for latency-insensitive queries, they fetch a large volume of data and thus consume a lot of bandwidth, and this affects the overall throughput of HBase badly. And we cannot wait to take them out. So to save HBase bandwidth from being exhausted, we just save a copy of this kind of data into an external Hadoop cluster asynchronously. Since these users don't need the data to be the most recent, the data copies will be buffered on local file system by saver until they reach a certain size or a certain amount of time. And the query engine will reject queries that acquire a lot of data. And the users can use the Hadoop client to query the data directly from Hadoop. And therefore, the error line for reading Hadoop is omitted in the chart. And before tuning for latency-sensitive queries, remember there is a case that 20% of data attracts 80% of queries. So we can find out what are these 20% of data and catching them in memory to make it faster to read. And so the first thing we need to know is what kind of data are interested. The first one is trend data, and especially for visualization, as we mentioned before. And it may involve any metrics. The second are metrics that are important to business, such as PV and the revenue. Their data are often used by anomaly detection. And the last is hot metrics that are frequently asked. it may be the matrix whose trend chart will be shown by default on visualization page when the page is opened. As for the trend data, here is the trend chart. And the blue line represents the raw data. And for example, most of the matrix collection cycle is 10 seconds. So there will be 60 raw data points within 10 minutes. And when rendering a trend chart in the front page, the raw data are fetched from HBase first and then aggregated to fit the chart span, just as the red line shown in the chart. So it means that only low-resolution data is necessary for trend visualization. And so to accelerate this procedure, we can just pre-aggregate the raw data points to reduce the amount of data to be fetched from HBase before visualization. And so we introduce a mechanism. Sorry? Something wrong? Okay, let's get back. And we introduced a mechanism called multi-level downsampling, and which pre-aggregate raw data points within a certain time window into an aggregation points. It's done by server in real time, and the aggregation point contains 4 statistics values. They are max, mean, sum, and count. And they are calculated from raw data points, which are in an aggregation time window. And we don't have to store average value because it can be calculated by sum and count. And server will write aggregation points into HBase at the end of the aggregation window. There can be multiple levels with different window size to meet different requirements. And the side effect of downsampling is that data of lower resolution is of smaller volume and thus can live longer. So, which means we can serve long-term queries. And in our TSDB, we have 2 levels of downsampling. As shown in the chart, the original database on the bottom left can be seen as at level 0. And level 1 and level 2 are 2 tables for aggregation data points. And table at level 1 stores points aggregated from those at level 0 and with a 10 minutes time window. And the table at level 2 stores points aggregated from those at level 1 and with a 60 minutes time window. And when querying, query engine can automatically adapt read to the table that at appropriate level according to the parameters. And in this way, a query of 1 year data for visualization can be finished in several milliseconds. And for another 2 kinds of data, we firstly distinguish key metrics and hard metrics. As for key metrics, a list of metrics can be provided by the users who value these metrics the most. And the hard metrics can be mined from the query engine's access logs. And the list of hard metrics will be refreshed every 3 months. And then server will write recent 12 hours of data of the metrics which are in the key and hard metrics list into Redis. And the list is called a caching list. When querying, query engine determines whether to access Redis by checking the caching list and the requested time range. For example, if you query data of a day ago, then they must not be in Redis. Data in Redis is also compressed in order to save more memory and to catching more metrics. The compression algorithm is from Facebook, thank you. And we modified it to meet our own requirements, such as to support our own custom data types. And the implementation is pretty lightweight. It only needs Redis as a dependency and is easily integrated with Server and Query Engine. You can find the paper of the compression algorithm in the link. But there are still problems. We noticed that HBase behaves badly under such a heavy load in our situation. And there are a lot of compactions and splitting which extremely decrease the overall throughput. And then the HDFS read and write latency is intolerably high. Here, I will not dive into HBase in this talk, but to make it clear, there are something you should know about first. And roughly speaking, HBase is a distributed data store based upon a log-structured merge tree. It will buffer all edits in memory in a sorted order, and then write them in batches into multiple H files. Since the edits are written to disk in an append-only way, which means the H file will never be modified, then you can view the H files as a buffer of all edits. When a read request comes, it may scan all H files to gather target data, and the amount of data being read is no less than the data that is actually needed. And plus, it would issue many disk 6 if there are many H files. And the compaction can merge smaller H files into bigger ones. Therefore, it reduces I/O and data amount of read. Then read can be accelerated by compaction. And about splitting, HBase stores rows of data in tables, and tables are split into chunks of rows called regions. A region will be split into 2 automatically when it reaches a certain size. And those regions are distributed and can be moved across servers to balance load. It is the essence that HBase can scale out. So, as compaction and splitting has so many advantages, so why on earth are compaction and splitting is bad? And compaction and splitting will dramatically reduce the overall throughput if not appropriately tuned. When we have more and more writes, there are more and more disk I/O and network bandwidth consumed by compactions and splitting. And when major compaction happens, HBase region server may encounter stop the word GC, and writes as well as region splitting will be blocked until the stop word GC is done. So that is intolerable. Actually, we can avoid the impact of compaction as well as splitting. And first, to avoid compaction, we divide data table into partitions according to the data point's timestamp. And the partition is actually an HBase table. And the time span of the partition is configurable. If we have 1 partition table per day, and then we can predict tomorrow's partition table size according to previous partition size. And then we can disable auto compaction to make sure major compaction only affects on old partitions. And these old partitions is unlikely to accept writes. And it only holds a part of all data. So the current partition won't be affected by major compaction. And the partitioning also brings us bonus. Since we can't store all data points forever, and points that are too old to be useful will be expired. And before we introduce partitioning, we set TTL on the data table, and data will be actually deleted by compaction when outdated. Now, with partitioning, we do not need to rely on TTL to delete outdated data. When data in the old partition are outdated, we simply drop the whole partition table without any compactions. And this extremely reduces the disk I/O. And then let's see how to deal with splitting. As talked before, after partitioning, the size of each partition is relatively constant. So we pre-split table into regions with equal key range. But it didn't work out later after the overall data scale has been increased insanely. Then we found out that the splitting is mainly occurred on a small set of region servers. And that is because some regions become hotspots. And you can see region 3, as shown on the top right. When we divide the regions into even key ranges, we expect them to be balanced. But it turns out that the keys with actual data distribute unevenly. And we can see region 3 holds the most actual data. So it's a hotspot. Since the load balancing is all about real data, so we can just divide the actual data into even size by their keys. And the keys list can be learned from the previous table partitions. And because the span of each table partition is constant, the actual data size of each table partition is constant too. And thus each pre-splitted region's final size will be constant. Then a region is less likely to split. And in addition to compaction and splitting, the HDFS read and write latency is also important for HBase's performance, and especially when there's a lot of writes and reads. When region server and the data node are on different hosts, they can only communicate remotely through the network, and it is very slow. And data locality is one simple but important thing that you should be aware of when tuning HBase network I/O performance. And to achieve a better performance, just put region server and the data node together on the same host. And as we balance the regions evenly by pre-splitting partition table, and there would be little rebalances across all region servers. Then the region server will likely to write data or read data from local data node. So pre-splitting makes it easier. Another problem is stop the word GCs in server. And unfortunately, our TSDB stack uses Java as the main language. And as the writes become more and more, and there comes a lot of GCs in server, and both minor GC and full GC. The former will consume more CPU, and the latter, full GC, will stop server from processing writes, which cannot be tolerated. And before increase the new generation size, we dive into the heap and find out that there are a lot of long-lived aggregation point objects, and that is the root cause of the 4GC. So as mentioned before, other than processing writes, saver is also responsible for downsampling. And it maintains at least one aggregation point in memory for each metric to calculate the 4 statistics values in real time. And these aggregation points live until the metric no longer exists. The number of aggregation points is correlated to the number of metrics. And so these aggregation points just occupy a constant amount of memory from the heap. Consider if we take this part of memory out of the JVM and for good, then they will never participate in GC, and then problem solved. So in saver, we allocate direct memory for the aggregation points. And the direct memory is also known as off-heap memory, and which is not managed by JVM, and thus it will not be GC'd. And more than that, these objects are reusable by leveraging object pool. And then we have more unused memory in JVM released by aggregation points. So we can enlarge the new generation size of JVM for incoming data points. And after all the tunings above, here comes the final architecture. To save the HBase bandwidth, we send a data copy to Hadoop, and we also design a multi-level downsampling for querying long-term data. And then we introduce Redis to catching the key and the hard metrics. And with the new architecture, the query response times 99th percentile decreased by 90% from more than 5 seconds to less than 500 milliseconds. And this architecture can support a doubled throughput. And then how we ensure TSDB's high availability? We deploy another TSDB cluster at a different data center as a standby, and writes are duplicated from the client side, while only one cluster is serving reads in the meantime. Whenever either of the two TSDB clusters encounters failure or is down, another TSDB can still serve. On single cluster failure, the API service will shift all the queries to another healthy cluster, and as Hadoop is an external service and is not for online use, we don't have to mirror it. And after a cluster is recovered from the failure, and if the failure has caused the loss of data, we can trigger a data repairing job to restore specific time series data from the healthy cluster. And in most cases, we just need to repair data of the key metrics. And within one single cluster, we provide multi-level data availability. It's actually a downgradation for read. If either of Redis or HBase is down, and the other one can still serve. And if the HBase is down, the Redis alone can serve recent 12 hours of data. And if the Redis is down, 80% of the query's response time will increase, but by a small amount. And for the same reason that we don't build a standby for Hadoop, here we also ignore the Hadoop cluster in the chart. And then about isolation. Baidu has a lot of businesses, and their monitoring data volume vary from each other, and also some businesses are more important than others, and some have much more surgent throughput. So if we put their monitoring data together into one single TSDB, they will affect each other. So we divide the TSDB cluster into subclusters according to its business identity, for example, product's name. And in this way, failures will not spread. Also, the businesses require different data TTL. And some important businesses require a longer data TTL, while others may only need a small TTLs. Since we can partition data by table, data table by date, we can also partition data table by business identity in one single TSDB cluster. And so that customized rotation policy can be applied to each businesses respectively. Okay, to sum up, in this talk, you see how we value a monitoring system at Baidu and how the monitoring system provides a billion time series. And we built a TSDB to store these time series. And as the data scale increases insanely, we face a lot of challenging problems. And by investigating these problems, we finally found out the reasons and then provide a series of solutions such as multi-level downsampling and caching and compression and partitioning of data, regime splitting, and some JVM's GC optimizations. They worked like a charm given such a heavy load. And we also introduced hard standby, a multi-level data availability and data isolation to ensure the TSDB's availability. Okay, hope it to be useful. Thank you.